Hello, and welcome. Thank you so much for the introduction. I'm Shelley Vohr. I'm a principal engineer at Microsoft based in Berlin. I've been working on the Electron JavaScript framework for the past about 8 years, as well as a Node core contributor for the past about 7. So today, we're going to be starting with the basics of garbage collection and how memory behaves in your programs. Then, we'll explore the algorithms that make it all happen and zoom in on V8, the engine behind Chrome and Node, to see how these ideas translate into practice. Finally, I'm going to be showing you what some of the more common issues developers experience are around memory and how you might go about fixing them. So, let's get started with the basics. What exactly is garbage collection, and why do you even care? So, in programming, we're constantly creating variables, objects, and data structures that take up memory. When we're done with them, we need a way to free up that memory so that it's available for other parts of the program. That's where garbage collection comes in. Garbage collection is an automatic process that reclaims memory occupied by objects that are no longer in use, helping keeping our apps from becoming memory hogs that could eventually slow down or crash. So we want to imagine our program as like a busy coffee shop. Every customer represents an object taking up space. If no one clears the tables after customers leave, there might not be seats for new customers or cups for them to drink from. Garbage collection is like that automatic cleanup crew that swoops in to clear out those empty cups and free up the space for new customers, keeping your shop orderly without you having to personally bus every table. As a higher-level language, JavaScript actually comes with garbage collection built in. You might think, great, OK, so then why do I care about this? Why is it my problem? And sure, that is actually one of the conveniences of working in JavaScript. You don't really have to manage your own memory. But here's the thing. The browser can really only do so much. If you're holding on to memory you don't need, all that garbage kind of just stays there, haunting your app like a pile of old code ghosts. So, while garbage collection is automatic, that's not always enough. If you want your app to stay clean, snappy, and ghost-free, understanding how garbage collection works can be important. Let's dive into it. I promise it's worth knowing. To get what garbage collection is all about, it helps to look at memory in 3 main stages. First up, we have allocation. This is where your program sets aside memory whenever you create variables, objects, or functions. You can picture this like booking a table at our busy coffee shop. We're reserving the space that we're planning to use. Next up is utilization. This is when your program actually uses that allocated memory to get things done. You can think of it like customers enjoying their coffee at the table. During this stage, the data is crucial, and if it suddenly vanished, everything would begin to break down pretty quickly. Finally, we have release. And this is where garbage collection actually comes into play. When the program no longer needs a given piece of data, it's like a customer finishing their coffee and heading out. The garbage collector is like the barista who spots the empty table, swoops in to clear out the leftovers, and then frees it up for the next round of customers. So, these 3 stages, allocation, utilization, and release, form the basic flow of memory management in JavaScript. Next, let's expand a little bit on what allocation actually looks like in JavaScript. We can start with primitive values, like numbers, strings, booleans, null, and undefined. Each one of these takes up a specific amount of space right when you declare them. So if you say const num equals 42, JavaScript is going to go out and grab just enough memory for that number and set it aside. But then we get to things like objects and arrays, which are a bit more flexible. So when you create something like letconf equals name www location Malaga, memory isn't just reserved for the conf object itself, but also for each of the properties inside it. Same with arrays. Say that you declare let colors equals red, green, and blue. JavaScript is going to allocate memory for the array structure and its elements, with enough space to grow or shrink as needed. And then there are functions. Functions in JavaScript are actually kind of unique. They're treated as first-class objects. So if you declare a function greet equals, or not equals, console log, hello world, JavaScript allocates memory both for the function itself as well as its code, ready to be used whenever you call it. So that's the allocation stage, reserving just the right amount of memory for everything your code might need. But it doesn't end there. Next, we have to actually use this memory. So once we've got our memory reserved, we're now going to need to use it. In JavaScript, utilization means working with the variables, objects, arrays, or functions we've already set up. Using let num equals 42, when you do something like num plus equals 10, you're using that value and thus changing it in memory. With objects and arrays, utilization involves interacting with and updating their properties or elements. If you change person.firstname to Shelley, you're using the memory that was allocated for that object in order to store new information. Or if you add an item to an array like colors.pushYellow, JavaScript makes sure that the memory was allocated for colors is adjusted to reflect that change. Once it's done, we've then got to be ready to clear that memory out. That leads us to the final stage. All right, so now that we've covered a bit of how memory is allocated and actively used in programs, the last stage of the memory lifecycle is releasing memory that is no longer needed. Without proper memory release, your program could eventually run out of space, and for extremely obvious reasons, nobody wants that. But here's the big question. How do we actually know when a chunk of memory is actually safe to release? Unlike cleaning up after a coffee shop rush, where you can easily tell when a table is done and ready to be cleared, deciding when memory is done is actually far less obvious. In fact, determining whether or not memory is ready for release is what is called in computer science an undecidable problem. In other words, there's actually no way to know for sure whether or not memory is fully safe to reclaim without potentially running into some issues. Before we continue, let's define an undecidable problem. In short, decidability is about whether or not there's a reliable algorithm that can always give us a clear answer to a problem for any given situation and do so in a finite amount of time. If such an algorithm exists, the problem is decidable. If not, it's undecidable. So I'll expand a little bit with an analogy. As you may or may not have noticed, I love an analogy. Imagine you're a librarian, and your job is to figure out whether or not a given book contains a specific story. If you have a straightforward system, like flipping through the pages or searching through a catalog, that will always tell you yes or no for any book, then that's a decidable problem. You know exactly how to solve it, and you know that it'll work every time. Next, I'll ask you to think for a second about whether or not there's a perfect set of rules to decide whether or not a given book will be interesting to every possible reader. You can't, right? Everyone has different interests, and those interests change over time. This is an undecidable problem. There's no universal algorithm that can solve this for every book and every reader. Determining when memory is ready to be released is similarly complex. There's no perfect algorithm to know for sure whether or not memory can safely be reclaimed in every scenario. To handle this, we use what's called a reduction, which breaks down this complex, undecidable problem into smaller, simpler, and more decidable pieces. First up is a more simplistic approach to reclaiming memory known as reference counting. In reference counting, each object tracks how many references point to it. And then when that count drops to 0, meaning no one's using it, it's considered garbage and is thus ready to be collected. But there's a catch here, and the catch is circular references. If two objects point to one another, their reference counts will never hit 0, even when they're no longer needed. This thus creates memory that can never be reclaimed. Reference counting also comes with significant performance overhead, as every reference change requires updating all possible counts. In applications with lots and lots of objects, this bookkeeping can pretty quickly build up and slow things down. So, while simple and effective in some cases, reference counting has limitations. That's why modern JavaScript engines rely on a more robust solution known as mark and sweep algorithms, which address these issues and are the foundation of essentially all modern garbage collection systems. So the current most common approach, as I've said, is now mark and sweep. Unlike reference counting, which checks if an object has references, mark and sweep determines if an object is unreachable, meaning it can no longer be accessed from anywhere in the running program. However, mark and sweep does have some trade-offs. Unlike lower-level languages like C, mark and sweep does not allow for manual memory release and can feel like a loss of control for developers accustomed to more manual memory management. Now, let's dive a little bit into how marking works in this process, where the algorithm identifies all reachable objects before moving on to the sweeping phase. In the marking phase, the garbage collector begins by identifying which objects are still reachable from the root. Essentially, objects that can be accessed, as I said earlier, directly or indirectly through the program's active references. This phase begins with a set of root objects, such as global variables, active function calls, or any other references that are still actively being used by the program. From these roots, the collector traces through every object that they point to, marking them as active. The key idea here is that if an object is reachable, it's important. So the collector ensures that all reachable objects are flagged as still in use. Any object that cannot be reached during this process is thus considered unreachable, meaning there's no longer a way for the program to access it, and it thus becomes a candidate for garbage collection. Once this marking phase completes and all reachable objects are accounted for, the garbage collector then moves on to the sweeping phase. This is when it clears out all the unmarked memory, effectively sweeping away all of the objects that are no longer needed, and then freeing up that memory for future allocations. This approach works pretty well in eliminating circular references and ensuring that only objects still actively being used by the program remain in memory. But there's more to explore in terms of the performance and complexities of these phases. So now that we've seen a little bit about how mark and sweep identifies and clears out unreachable memory, we can explore how modern garbage collectors combine these strategies and more to handle complex applications efficiently. So I've now covered some of the basics of common garbage collection algorithms, but how does that actually apply to JavaScript in your browser or in Node? For today, I'm going to be focusing on V8, the engine behind Chrome and Node, and some other things, but we can focus on Chrome and Node for now. Some of you may be familiar, but just so we're all on the same page, V8 is the engine that takes your JavaScript, turns it into machine code, and then keeps optimizing it while your program runs. V8 uses a mark and sweep garbage collector, identifying reachable objects, and thus sweeping away the rest. To stay fast and efficient, it performs much of this work parallel and concurrently with JavaScript execution, thus avoiding major pauses. It's also incremental, breaking large cleanup tasks into smaller pieces to prevent your app from freezing up. The goal is simple. We want to keep memory clean without you or your users ever noticing. So the way that V8 garbage collection works hinges on what is known as the generational hypothesis. This is a two-part hypothesis based on a few observations about how memory behaves in most programs, especially ones with dynamic memory allocation. It's the idea that most objects die young, and those that don't tend to stick around for a very long time. In JavaScript, we're often creating lots of short-lived objects. Think about arrays for quick calculations, temporary DOM nodes, or objects used only within a single function. These objects are often created and then pretty quickly thrown out. Since they don't stick around for long, it's pretty efficient for the garbage collector to check them frequently and then throw them out when they're no longer needed. Objects that do survive for a while, like application-level data structures, event listeners, or single-page application states, often stick around for the lifetime of the whole program. Once these objects survive a few rounds of garbage collection, the garbage collector realizes that it doesn't need to check them as frequently. They're less likely to become garbage and are then moved to a generation that is collected less often. To implement the generational hypothesis, V8 organizes its memory into different regions, or generations, in what's known as the heap layout. This setup lets V8 treat short-lived and long-lived items differently, optimizing garbage collection for each type. I could drill down into exactly what this entails, but I only have so many minutes, and we'd be here all day. So all you really need to know is that V8's garbage collection strategy is all about balance, collecting short-lived objects frequently to be able to free up memory quickly, and then long-lived objects much less frequently, but with more attention to memory layout. V8's garbage collection is a pretty well-oiled machine, but even the best systems can't fix every problem. That is where memory leaks sneak in. A memory leak is like leaving the sink running in your app's memory. Water is flowing, but no one's there to use it. It's memory that's allocated and then never properly garbage collected. Over time, those leaks can flood your app with unwanted, wasted resources. The result? Increased memory usage and degraded performance that can compound over time. There are a lot of ways to leak memory, so for today's purposes, we're going to be spending our time on 4 of the usual suspects. These are accidental globals, timers, detached DOM elements, and time closures. Each of these hurts your garbage collector's ability to do its job properly, as well as your end user's ability to use your app smoothly. The good news, however, is that they're all extremely fixable. The first of these is accidental globals. In this example, because session data has been assigned here without let, const, or var, JavaScript interprets session data as a global variable, even if create session is called from inside a function. That means that session data is accessible throughout the entire program, and not just within create session, as you might expect. This accidental global variable sticks around in memory for the whole lifetime of the program, since the garbage collector can never identify it as unreachable, even when the function completes. If create session is called multiple times, such as each time a new session starts, session data may end up overwritten, but never fully removed, potentially keeping unused data in memory and causing a leak over time. To fix this issue, we'd want to make sure we declare session data with either let, const, or var to ensure that it's scoped correctly within create session. With this fix, the variable will then be scoped to create session, so it'll be eligible for garbage collection when the function call completes, and the memory will be freed accordingly. Next up, we've got bad closures. In this example, make closure creates a large array called data and then returns an anonymous function that logs that to the console. This return function forms a closure, capturing the data variable in scope. Since the function keeps a reference to data, the array won't be garbage collected, even after make closure finishes executing. As long as the closure variable exists, the closure will retain data in memory, keeping this large array allocated. If make closure is called multiple times, each new closure will keep a separate large data array in memory. Over time, this can add up, which causes the program to consume more and more memory. To avoid memory leaks with closures, You should avoid creating closures with functions that are executed frequently or that are long-lived. You should also make sure that they only capture the variables they actually need. In this example, if data is only necessary temporarily, then we should release its reference to data as soon as it's been used for what we need. Next, timers. In this example, start timer creates a large array called data, and then sets up an interval timer with set interval that logs timer running every second. The interval function has access to the variables inside start timer, including data due to closure. The set interval callback forms a closure over data, meaning it keeps a reference to data as long as the timer is running. Since set interval will never automatically stop, the timer will keep executing indefinitely, preventing data from being garbage collected. Over time, as before, if set timer start timer is called multiple times, then each call will set up a new interval, each with its own closure over a separate data array, causing significant memory buildup. To avoid this kind of memory leak, we should always be sure to clear timers when they're no longer needed. You can use clear interval to stop the interval, which releases the closure and allows the data to be garbage collected. Alternately, you could release data, as we did before with closures. Finally, we have detached DOM elements. In this example, we use a map called element map to associate a DOM element with some large data. This map allows element to serve as a key, storing data as its value. After attaching the element to the DOM and then adding it to the map, the element is then removed from the DOM, simulating a case where the element has been discarded. Even though the element has been removed from the DOM, it still exists in memory because it's still being used as a key in element map. Since JavaScript map objects strongly reference their keys, the element and data will both remain in memory. If this pattern repeats, with elements added to the map and then later removed from the DOM without being deleted from the element map, a memory leak will grow over time. To fix this, we should always be sure to remove any DOM elements from the map at the moment they are no longer needed. When we suspect memory leaks or inefficiencies, like those we've just spent some time going over, that is where heap snapshots can come in. A heap snapshot is like pausing your app and taking a detailed picture of everything currently in memory. They let us look directly at what's in memory at specific points in time, helping us identify objects that stick around longer than they should and pinpoint memory leaks in our code. With tools like Chrome DevTools, you can capture these snapshots and dig into the objects, references, and variables your program is holding on to. So what can you do with a heap snapshot? First, it helps you understand memory usage by showing exactly how much memory each part of your program is currently using, like a memory budget report. You can also diagnose memory leaks by comparing snapshots over time. Persistent objects that shouldn't be there are going to be the prime suspects. Snapshots let you explore retainers to see what's keeping objects in memory, like lingering event listeners or caches. Finally, they help you optimize performance by cleaning up unnecessary references and removing memory overhead. The heap snapshot pane in Chrome DevTools makes it easy to analyze memory allocation, track retained objects, and pinpoint areas to improve. So, as we've seen, leaks often come from how objects and references are managed in our code. The next step is learning how we could potentially prevent those problems from happening in the first place. And that is where certain JavaScript features can actually really help us out. JavaScript provides a few designed to help us manage memory more effectively, even in complex dynamic applications. Let's start with weak maps, which function similarly to regular maps, but with one critical difference. Their keys can only be objects, and those keys automatically vanish from the map when no other part of your code is holding a reference to them. This makes weak maps perfect for use cases like caching or managing private data tied to objects. For instance, if you're storing metadata about DOM nodes in a single-page app, a weak map ensures that once those nodes are removed from the page, they're eligible for garbage collection. This prevents memory bloat and keeps your app efficient. Here, you can see another solution to the DOM node memory leak we saw before, which uses a weak map, and thus doesn't need to remove the element from the map explicitly. Next, let's look at weak sets, which are like sets, but specifically for object references. Weak sets can actually only store objects, and if no other code references those objects, they're automatically removed from the weak set. In this example, user1 is added to the weak set, and then when user1 is no longer referenced, it can be garbage collected automatically. The weak set does not keep a strong reference to user1, so there's no risk for memory leaks. This makes weak set an excellent tool for memory safety when you need to track objects without holding onto them unnecessarily. Unlike regular sets, weak sets don't support iteration or size checking, which does make them less suitable for general-purpose data storage. This last one I threw in here not because I necessarily think you should use it, but more because I think it's interesting. So, a finalization registry is a tool in JavaScript that lets you run cleanup logic whenever an object is garbage collected. It's something that someone might use when they're tracking resources that might need explicit cleanup, but are hard to manage directly. For instance, it can close open files, clear caches, or disconnect from external resources associated with the object. Sounds nice, right? But actually, it should really just be reserved for situations where explicit resource management is not feasible, and you need a kind of last resort cleanup. Beyond that, you can use patterns like try, catch, and finally, which enable more deterministic memory management by guaranteeing that the finally block will be run at the end of any arbitrary logic. So garbage collection might not be the first thing you think about when you're writing JavaScript, but giving it a little bit of extra attention can lead to stronger, more efficient code. Start by considering the lifetimes of your UI elements. Cleaning up lingering references when elements are removed helps remove memory leaks. Regularly profiling your heap with tools like the Chrome DevTools heap snapshot pane can reveal hidden issues and help keep your app running smoothly. And don't forget to watch out for globals. Long-lived variables can hog memory for longer than you intend. By working to solidify these habits, you'll write faster, more reliable apps and take full advantage of JavaScript's memory management capabilities. Thank you so much for listening. I hope you found something useful to take back to your projects. Find me afterwards for any questions you might have and around the internet on GitHub, Twitter, and Blue Sky.